edges than G
Not in that set. If you add,
is not an S set, and thus must have a Hamiltonian cycle. I guess, so, well, you know, I shouldn't say that. I don't need that right now. This G is a graph, that's not totally true what I just said, but if you add an edge to G, then it will have a Hamiltonian cycle. That's actually what I want to do. So, yeah, so, okay, so I have this connected graph. Here's what I know about this. It has G has n vertices. Each vertex has degree greater than or equal to n over 2. It's connected, and it has no Hamiltonian cycle. I need to show that this entire thing leads to a contradiction, right? If I can show that this leads to a contradiction, then there is no graph G. There is no such graph G, and so this set must have been.
Are you trying to show like, are you trying to show that there is no graph G such that adding any edge creates something that has necessarily a Hamiltonian cycle?
That's exactly what I'm going to talk about. Yep.
Wait.
Yeah.
Wait.
I'll say that one more time when I get to it. What's that?
What if G just has infinite number of edges?
You can't have an infinite number of edges. Simple graph.
By
It's a simple graph with a finite number of edges.
Wait,
So in fact, I'm establishing this argument for each n. Is really what I'm doing.
when you add an edge, does it disrupt?
An arbitrary. What?
When you add an edge, does that disrupt? How do you know you can construct an HC?
Yeah, it's not obvious at all. I'm gonna do this. That's why this is a hard group. Okay. So so if G is complete, then it. So I'll just write something down. So if G is complete, then G definitely has a Hamiltonian cycle. Okay. So G must not be complete. So G is not complete. Whoever's manning the camera, you're getting all this?
Yes.
All right. All right. Well, if G is not complete, then take two vertices which are not connected. So take two vertices which are not connected. Which are not connected, and call them W1 and Wn. Okay, so these are two people in the town who are not friends with each other. Good. All right. And here's the key thing. If they should suddenly become friends, if they should suddenly secretly become friends, then we have a Hamiltonian cycle. So yeah. So if we connect, or if we add an edge, I should say, if we add an edge connecting W1 and Wn, that graph, let's call it G, or let's call it G prime, must have a Hamiltonian cycle. Because G prime is exactly like G, just with this new friendship between W1 and Wn, right? And now, this is a graph which still meets the condition, because we're simply adding friendships, and yet it has more edges than this graph G did, right? But G was the graph with the most possible number of edges and still no Hamiltonian cycle. So if I add one more edge to this graph, then it'll have a Hamiltonian. Everyone cool? Yep. Okay, so, yeah. So, G prime has a Hamiltonian cycle. And I can even say something more about the Hamiltonian cycle in G prime.
It has to use the edge.
Yes. Furthermore, the Hamiltonian cycle in G prime uses the edge W1, Wn. Because if it didn't, then that would just be a Hamiltonian cycle in G, which we know there isn't. Cool? Okay. So the rumor, so basically what's happening is you have a town in which, we're supposing that we have a town rather, in which you can't do this rumor thing, right? But then suddenly, secretly, two people that we didn't think were friends become friends with each other. Now we know that there is a way to do that rumor. All right, somehow this is all supposed to lead to a contradiction. Okay, so we do. So G prime has a Hamiltonian cycle. And let's say that Hamiltonian cycle, also by the very nature, do you guys just get this?
No,
It's going to be like forever to even understand
For
this.
your town analogy, isn't it that like any two people who aren't yet friends could become friends, and then a cycle would exist?
Yeah, those are an
Yes.
arbitrary.
So it's like,
Yes.
okay.
Yeah.
So it's not just like there exists two specific people. Right?
No.
It's like for any
Correct.
two people
Yeah,
who are friends.
Is that true? Yes. In this situation, which by the way is contradictory, so we're in the absurd world here, but in this situation, we have a town where there's a bunch of friendships, quite a lot of them, but still no way to complete, to make the Hamiltonian cycle. And what we are now going to, and also by the way we've structured this, if we pick any two people, you're right, who are not friends with each other and make them friends, suddenly we have a graph now which meets the condition yet has more edges. So it can't be in this graph, and so it must have a Hamiltonian cycle. So he's correct. If any two people become friends with each other, then we get the Hamiltonian cycle.
So the absurdity of this comes from the maximum number of edges thing? Is that?
What the absurdity, the contradiction is going to come by me showing, it's going to take 10 minutes, that there was a Hamiltonian cycle in G after all. Okay? It's not much use. Okay, let's go. So G prime has a Hamiltonian cycle. What does this Hamiltonian cycle look like? Well, it doesn't matter where you start a cycle, because it's like a cycle, right? So we just go W1, W2, W3, all the way, Wn minus 1, Wn. Okay, so let's make a picture of the cycle. It goes like this. Here is W1, here's W2, here's W3, W4, etc. Okay, dot, 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 dot. And then over here we'll get the Wn, and over here we'll have like Wn minus 1. Okay, so the cycle, so this is the way the rumor actually spread. The rumor spread, oh, so wait, we should, kind of screwed this up in third period, my crappy story. So let's suppose that W1 has a secret, So this guy has a secret to tell. And W1 tells his secret or her secret to W2. And here's how secrets work. W1 says to W2, please don't tell anyone else. We're friends, but I don't want anyone else to know. Alright, what does W2 do immediately next? W2 tells more people, because that's how secrets work. And when W2, but here's the crucial moment. Here's the crucial point in understanding the analogy. When W2 tells the secret to W3, what does W2 want to do as W2 is telling the secret?
Ruin his friendship.
No. What do you do when someone tells you don't tell anyone else and then you do tell anyone anyway?
Kill the really don't.
Yeah, then W2 says in a fit of total, what's that word? Hypocrisy. Yo, W3, don't tell anyone else. And especially, whatever you do, don't tell Wn, right? Because then Wn would know that I've been telling, because Wn is the person that the secret's about. Like, maybe like Wn's like, like W1's secret is that he's in love with Wn or something like that, right? The secret involves Wn somehow. So it's like, don't tell Wn. Okay, anyway, and this keeps going, and this keeps going, and this keeps going, and eventually it does get all the way back around, and Wn tells W1, and then W1 realizes, oh my god, everyone must know, the whole town, and you know it's terrible. Okay, that's what happens. Alright. Well, so Wn is the like, sort of the object of the, I don't know, the analogy is kind of breaking down a little bit. Screw the analogy, let's just do the math. You don't like the analogy?
No.
Okay, the math. The math goes like this. Consider, in order to produce this sort of contradiction, and this is just Gauss's proof, just me trying to explain it a little bit better. Consider this at B. B is the set of all vertices in V such that Wi is friends with, or there's an edge between Wi and Wn. Okay. So set B is just, this is just the friends, this is just the set which is the friends of Wn. Okay, and note that, the edge refers to the edges of the original graph G, not G prime. Okay, so first of all, note that Wn is like not in this set B, because you can't be friends with yourself. Because it's a simple graph. Okay, good so far. Okay, then this is the graph that it's a little bit more difficult to get your head around. So now consider the set of all vertices, which such that the next person that they told in the Hamiltonian cycle that exists in G prime is friends with W1. Okay, so these are simply, this is simply the set of, no, it's not simply the friends of Wn. This is, okay. Well, actually, it ends up being just the friends of W1. Because in the Hamiltonian cycle, every vertex is in there. No,
That's definitely not the friends.
The friends of the friends.
No, it's
Well, so, wait.
So here's what it is.
You've already
It's-
made a Hamiltonian cycle now?
Yes. Well, in G prime, the
Yeah,
Hamiltonian
you
cycle
made
is
the G prime. Okay.
Yeah, and so that's what this is referred. The I plus 1 refers to the person that I told. So okay, I think this is the best way of thinking about it. Each person, as they are about to tell the secret, has to worry whether the secret will get back to W1, right? And so basically, F is the set of people which, as they are passing the secret on, have to worry about the secret getting back to W1. Okay, because, for example, maybe W2 tells W3 the secret, right? And W2 says, yo, W3, don't tell W1. And W3 is like, yo, I'm not even friends with W1. So I'm definitely not going to tell W1 that you're telling me, right? But sometimes W3 is friends with W1, and so W2 has to worry about whether W3's secret is going to get back to W1. Follow? So this is the set of people who have to worry as they're telling this, as they're passing on the secret, whether it will get back to W1 or not in like the very next step. You with me? Okay.
So
Fine.
one step mutual friends.
Kind of like one step mutual friends, but specifically not just one step in general, but it's the next person, it's the person they're telling the secret to. It's the people who, as they're telling the secret, have to worry about the secret getting directly back to W1. Okay, so another fact is that Wn is not in F either, because Wn plus 1 is just W1, right? So this is true because it's a simple graph, right? Because there are no loops, because W1's not friends with it himself. Are you with me? Okay, so since that is true, then what this means is that if I union these two sets together, that has to be less than n. Because I've just given in a particular vertex which is not in either of those two sets. That's Wn itself. Wn's not in there because you can't be friends with yourself, and Wn's not in set F because if it were, then that would be saying the person that, well, I think this is clear, right? Because W1 isn't friends with itself. Okay, good. All right, furthermore, says me, oh, this is the hard part. So let's just look at this. This has to be less than n. So what is the size of B union F? Well, by like a simple inclusion-exclusion, it's like the size of B plus the size of F minus the size of B intersect F, right? Okay, and what is the size of B?
The degree of...
The size of B is simply the degree of Wn. This is the degree of Wn, because it just is all the friends of Wn. And what is the size of F?
Every single thing that's
the degree of-
so it just is the degree of
Yeah.
W1.
It's the degree of W1, because you're in this set if you're friends with W1, and every vertex is somewhere in the Hamiltonian cycles. Okay, so I really want to know what B intersect F is, and it turns out it's a 0, the size of this set. Okay, so claim B intersect F is empty. Or I guess I just do this. B intersect F is empty. Okay, why? Well, suppose that there was something which is in both B and F. So suppose WK was in B and WK was in F. Okay. So what that means is we have some vertex over here somewhere, WK, and then there is like the next guy, WK plus 1. And this WK is in F and is also in B. All right, what does it mean for WK to be in B? Well, it just means that WK is friends with WN. So WK is one of the people who might have gone directly to WN with the next. Okay? But what does it mean for WK to be in F? For WK to be in F, it means that the person that WK told their secret to was friends with and hence might have fibbed back to W1. Okay, but this is impossible because in blue is the Hamiltonian cycle that actually happened in G prime, right? I'm putting some dot dot dots here, right? In the actual G prime, we went from W1 to W2 to W3 to W4, eventually we got to WK, then WK plus 1, eventually we get to WM minus 1, WN, and back to W1. Okay, so what we're now doing is we're supposing that there exists a vertex which was both friends with WN and the next person they told was friends with W1. Does anyone see why this is impossible?
You already had a Hamiltonian cycle before you added the edge.
Then you already had a Hamiltonian cycle, says Alice, because you could have just, like not, I didn't need this guy at all, right? Because I could have gone from W1 to W2, from W2 to W3, from W3 to W4, to WK, and then instead of WK telling WK plus 1, WK could have gone to WN. Did I do that right?
Yeah, and then just go down and then.
Oh, yeah, and then backwards, right? Because these guys are all friends. And then when I got here, back up to W1. So in green is a Hamiltonian cycle. You see that? Which does not involve this WN to W1 edge, which we added in the transition from G to G prime. But by assumption, G did not have a Hamiltonian cycle. So if this set was empty, or if this set was if there was something that was in both of these sets, then we would get a contradiction. Follow? Okay. So conclusion is that so I'll just write contradiction. Well, I didn't even do a supposition. So I just have that this is empty. So B intersect F is indeed empty. So that means that this is just 0. So what we have is that B union F has to be equal to the degree of Wn plus the degree of W1. But this I know to be greater than or equal to n over 2. And this I also know to be greater than or equal to n over 2. So if I add two things together that are greater than n over 2, I have that this set must be greater than or equal to n. But I also know that it's less than n. Wait, that didn't work. No, it did work. Yes, because n is greater than n. Okay. So many things happened. I made these two weird sets. I showed that there's something which is not in either of them. So the total sum of the sets has to be less than all the vertices. If each of the people who these sets were constructed to be the set of people friends with has enough friends, then altogether that set has to have at least n friends. There have to be at least n people. And also there's no overlap. That's essentially the contradiction. And since we get this contradiction, that means the contradiction resulted from our assumption that there was some graph G in this set at all. And because of that contradiction, there's actually nothing in that set. And so that set is empty. And so it's impossible to meet that condition without. It's WAP-ish. I don't think I'm ever actually using the WAP. I am.
Basically, you're saying that there is no. Well, most is basically at least, right? And so
Yeah.
Isn't WAP really like
And so then
it's
becomes
finite, so like it's fine.
I think everything's finite, so the WAP isn't relevant. Yeah, I also thought the WAP was relevant. Alright, cool. I thought that proof was pretty hard. I hope that went pretty well. The analogy broke down a little bit. Anyway, class is over. Good. Next class, Thursday, don't miss. Many exciting things are happening.
All the juniors.
All the juniors are going to be absent. It's very sad for you. We're going to do fun things that are involving all kinds of things. Good. Okay, bye, people at home.